Hi, my name is Hamid Jamshidifar. Today I'm trying to show you how to find the internal forces. By the internal forces and moments, I mean that, for example, we have a beam like this one, which is fixed to the wall, and we are cutting through a point like B, and we are interested to know what forces do we have in point B and what are the moments that we may have at the point B. And the reason for that is that when we are designing different mechanical structure like this one or other ones like a bridge, we are interested to know how much are the moments and the forces in different points of such structures, meaning that if we have a failure is because of these internal forces, and we are interested to know how much are these things at that point, and finding these forces and moment could help us to have a better understanding of the points which we may have the maximum loads on that. And the idea is to design these structures in a way that we can tolerate these forces and these moments. That's the goal. But here in this session, I'm trying to show you if we have a point like B and we are interested to know what is the forces there and what is the moment there, how we can find it. Okay, I start with a couple of examples. Before that, I just want to show you that the idea is the same as before, meaning that because we are talking about the planar problems, at most we can have three unknowns. For example, here if I cut here, if I know P1 and P2, this part of this structure has a free body diagram, meaning that if I cut through this, I need to put whatever is applied by the other section to this. Because this is a like continuum beam, it can apply two forces. We name this guy normal forces, this one shear force or vertical force, and this is the moment. It's like a wall. When we are attached to a wall, and when we remove that in the free body diagram, we put this. But just consider this right part and forget about the left part. Here I have free body diagram of single part. This is static, meaning that we have all the parts in the static equilibrium condition, and three equations for each one of these guys, meaning that if I solve this, I have three equations, and I can find three unknowns here. If I can find these three unknowns, these are also obtained. The point that we need to be careful about is the direction of the moments and forces here. Whatever we obtain here is exactly here with the reverse direction, because these are action and reaction forces and moment. And by having these ones, we can find this. This is the idea, and everywhere I'm trying to show you how to match the number of unknowns with the number of equations. Okay, let's get started. Oh, before going through the examples, I want to show you what are the positive values when we are cutting through a beam, and how we define those things. As long as we have a tension, and for the axial forces, we name them positive normal forces, meaning that if you are on the right side of a beam and you are here, the normal force is to the right. The same story here. These two are positive. The same story here. These are making tension, and just make this guy elongated, increase the length of this guy, and that's what we name positive. For the shear, it's like going from left to the top and get down. This is the positive. We set this positive direction for the vertical forces or the shear forces, meaning that as long as I cut and I have a force like this on the right side of the surface which is cut, as soon as it is downward, we name this positive. The same story here, this is positive. Then when we are on the left side, this should go up. When we are on the right side, this should go down. These are positive. And moment is like this. As you can see, these moments are making this beam like a concave shape, and we name these guys positive. And as long as you have a picture like this one and you are on the right side, this is positive. And when you cut through a surface like this and you are on the left side, this is positive. We need to keep these things in our mind and use these standard positive forces and moment for solving the equations. Okay, here I have a question. I want to show you what are the internal forces at a point like B. The first thing that we need to notice is that do we need to find the reaction forces at point A or not? Here I would say we don't need that, because if I cut through this point, I would have three unknowns, including the normal force, the shear force, and the moment or the bending moment. And all other things are known, meaning that I have a distributed load which is completely known. Then I don't care how much the force is here, normal or shear, and also the moment, because I can cut through this point and make a free body diagram with three unknowns. Then this is the idea. I put point B over here and I have a distributed load like this one and three unknown forces. For the unknown forces, I put a normal force at B, a vertical force at B, and a moment like this. You may ask that how I realized the direction of these ones. This is arbitrary. You can take whatever direction you like. But the idea is like this. All of these forces are pushing down this part of the structure. Then we need to have a force to prevent this motion. Then VB should be upward. And if you take the moment around this point, these forces are going through that point and making no R around that point. And if I put my finger here, this structure, because of this distributed load, is going to rotate clockwise. And the only thing which can prevent that motion is M. M should be counterclockwise, and that's why I'm putting this M counterclockwise. By the way, it's arbitrary and you can take whatever you like. Okay, as you can see, what I have a distributed load and I need to deal with that. For dealing with the distributed load, you can divide it to two things. Actually, I have one rectangle over here and one triangle on the top. I can make it, for example, yellow, and I can say this is 200 and this is 3 and 3. I can say the value over here is 100, meaning that the blue part is 100 Newton per meter, and I know this length is 3, and I know this part is also 100 Newton per meter. For solving the reaction forces, we replace each one of these distributed loads with a single load. As you can look at the unit of the distributed load, it is Newton per meter. It should be multiplied by a length like this guy to have a unit of Newton. And that's the way that we solve it. Meaning that right now I have a rectangle here with the blue color. I just put, instead of that, I just put a single force, which is 100 Newton per meter times 3 meter. And it would be 300 Newton. As you can see, it should be a force, and the unit of the force is Newton. The same story here, but we have a rectangle. We have a triangle. The triangle story is a little bit different. When we have a triangle and distributed load like this, and let's name this guy A and B. We replace this force with a single force in 1/3 of the length, meaning that it would be the area of this, which is AB over 2. This is the magnitude of the force. And the length is like this. If the total length is B, this is 2/3 of B. And this is 1/3 of B. This length. Then instead of that single triangle, I just put a force here, which is 100 times 3 over 2, and the unit is Newton at the end, and this would be 150 newtons. And I know this is 1 meter, and I know the blue one is in the middle, 1.5 meter. And right now I can put the reaction forces and solve that. For the reaction forces, I just put them there, and I know this should be upward VP. Right now I can write down the equations, including sigma fx equal to 0, which gives me NB equal to 0, because I don't have any other forces in this direction. I have just NB, it would be 0. After that, I solve for the vertical force, sigma Fy equals 0, gives me Vp minus 300 minus 150 equal to 0, which gives us Vp equal to 415 Newton upward. And the other thing is sigma m, which I prefer to do around point P, equal to 0. And the only thing that I have, and we consider counterclockwise positive, and solve it for m. I have m, which is counterclockwise, and minus 300 times 1.5 as the r, minus 150 times 2 equal to 0. And if we solve this guy, that would be m equal to I have 300 and 450, which means 750 Newton times meter. This is the total moment over there. And at the end of the day, I know that if I do the free body diagram of this part at point B, I have no force, no axial force, and a vertical force of 450 and a moment of 715 newtons time meter. And this is the way that we solve this. Okay, going to the next example. I have another example here. At the beginning, I just tried to do the cut and show you why we need to solve the whole free body diagram at the first, step and then go for the cut. But let's do the cut together and see what is happening. The question here is whether the internal forces at point B. If we cut over there, what I would have is like this. I have a roller over here, and by cutting through point B, I have three unknowns over there: NB, VB, and M, which is like this. And I know that 200 Newton meter is applied at the end, and instead of this roller, we need to put the forces which is applied on that. Because it's a roller, I just put CY. It cannot apply any force in the X direction. And as you can see, we have four unknowns. We have four unknowns, one of them moment, and two forces here and another force here, and we cannot solve this. And the idea here is that we know that we can solve the whole structure at first and then go here. By solving the whole structure and knowing that this is in a static equilibrium condition, we can find this force and then solve the whole structure. And let's do the free body diagram of the whole structure together. As you can see, we have a y and a x because we have a pin over there, and also cy at the point C, and 200 Newton meter here. Right now I can write down sigma of x, sigma of y, and sigma m, all of them equal to 0 for this free body diagram of the whole system. And by solving these equations, I can get cy. You can solve only one of them. If you take the moment around point A, ax and ay don't have any arm, and you can find your cy and bring cy here, and then write down three brand new equations for this part of the structure and solve them, and you match the number of unknowns with that. And here you can start by sigma m around point B and get rid of the unknowns over there, and then sigma of x would be helpful, and then sigma of y. I just review another example here which need you to find the reaction forces at the beginning. Here, if I do a cut over C, and I need to cut through all the structure, I don't have the forces at point C. Actually here, let's assume that P is given. If I know P, because of having a cable over here, I know when I cut through this, I have P over here as well. Meaning that we don't need to know we don't need to solve the whole structure at the beginning, and it's fine to go ahead with this cut. And if I do the free body diagram over here, what I would have is something like just covering this part, and I'm just putting the reaction forces. I would have Cy, or sorry, V at point C upward, N at point C, and also M. And I know this is P because it's a cable. P is known, and three unknowns over here, and three equations: sigma of x, sigma of y, and sigma m equal to 0. And right now you can solve this. As you can see, finding the reaction or internal forces at a point is not that hard. It's very similar to the problems that we have solved so far, and the idea is just doing the whole free body diagram at the beginning in some problems, or just cut through the structure and try to find the matched number of unknowns with the number of equations. In the next video I will show you how to find the diagrams of these internal forces, meaning that the diagram of the shear force and the diagram of bending moment. And you need to be careful. This moment is named bending moment because it's bending the structure. And this force is shear force, and this is the normal force. These are the names that we would use usually in the next videos. Okay, have a good day.